All right. November 8th, 8 a.m., Physics 213, Fall 2016. A couple of announcements. One is, and it doesn't really affect you at all, the Chancellor investiture is Thursday afternoon. Now, for the most part, none of you are affected, but there are a few. Talk to Dan Miller. There's one lab section that's gonna get not canceled's the wrong word. What's gonna happen is that all the members of that particular lab are gonna move into other labs. So talk to Dan, he's in charge. If you're not in that lab, go to lab. It's that simple.
What lab type?
Huh?
What lab type?
If you're not, if he hasn't contacted you, you're not in that lab. So then go to lab. There is the Thursday 4 to 5:15 class has been canceled. Not by me. I've never canceled a class. I've attended every class. But because of the afternoon class being canceled, what's going to happen is I've given them a choice. They attend the morning lecture or they watch the morning video. So there will be a noticeable increase in attendance that day. So let me get this thing all straightened up. And of course we have our Tuesday morning garbage pickup. Lovely. So those are the brief announcements. The next announcement is new material today and Thursday of this week. The review session will be the Tuesday lecture, and then the test will be Tuesday, or I'm sorry, not Tuesday, goodness, Thursday, 8 to 9:15 here. So a week from Thursday, you're taking your test in here. Now, the usual suspects of excused absences. I was in a coma. I'm contagious. I'm going to try out for the NFL. Stuff like my parents suddenly got me a cheap airline ticket. I've got to take the test on Wednesday. This test has been scheduled since March. We do not accept airline tickets as excused absences, so you got to take that test. In fact, if you live in Jackson, you could take the test on Thursday, walk home, and still be in Jackson by Thanksgiving. So it is, don't give me any of that nonsense. All right, now.
Dr. Eschenberg?
Yes.
Would you be able to post the like the practice tests this week? Or
The practice tests I do have on my desktop. I'll post them today probably.
okay.
Yeah, right now I'm looking at the test pack, the summer 16 and the spring 16. Maybe the summer 15, but I'm not sure. These two will be enough because that'll get you a good idea. For fun, maybe fall 16, because that has the infamous bucket of brains. The bucket of brains problem. That was the last fall. Someone wanted a Walking Dead theme test, and I obliged them. So. Oh, I'm sorry. That would be this one. Thank you. It's still early. Physics at 8 a.m. is rough. All right, so there'll be a whole packet of stuff that we can take a look at, and we could start reviewing on the tutorial on Friday 1 p.m. in Bishop. That may go a little bit long. Because at Bishop, what we normally do is we go over the homework, and if you got any questions about old test questions, that's another good time to do it. All right, we're doing good. Okay. Now, just as a review of what these tests are, about a week before we just go over the usual stuff. This is our third test. We should be familiar with this. 25 multiple choice. One appetizer problem, which is 5 points, 3 15-point problems. So for a total of 100 points. As for what the appetizer problem is, I have no idea. As we get closer to the test, it'll probably solidify a little bit, but the format's still the same. The test will be geared average student, should be done in 60 minutes. Max time 1 hour and 15. And for the most part, those times have been working out right. You always get those early ones at about 40, 45 minutes. The bulk of the students start handing in at an hour, and then you've got those people that you gotta pry the tests out of their cold, dead hands at about 1 hour 15. So it all works out to be the same. Now what we're gonna do is, last lecture we talked about oscillations, and we talked about pendulum. And with oscillations and pendulums, the two main ones that we study are spring pendulum and simple pendulum. And with the spring pendulum, that mass can go back and forth, has a spring constant, and it has a mass. The simple pendulum has a length, and it goes back and forth. And we went over the period of the spring pendulum, and we went over the simple pendulum, and so we went over why these things are the way that they are, and so we brought up some interesting ideas. So the first off is the spring pendulum mass dependent? Is the spring pendulum mass dependent? Yes. Why? Because mass is listed in the equation. If I quadrupled mass, what would happen to the period? It would double. So if I quadrupled that mass, what would happen to the frequency? It would be, well, what he said. Is that what your answer is? It would be cut in half. Why? It's in the inverse. The relationship between period and frequency is what? Don't look at the board, look at me. Frequency is 1 over t. What are the units of frequency? Hertz. Another way of saying hertz is inverse seconds. Good. For a spring pendulum, the period is 5 seconds. I take this spring to the moon. Nothing changes except for the fact that gravity has been cut in 1/6. What is the new period? I'll repeat myself. The spring pendulum, when measured, has a period of 5 seconds. I take it to the moon. The moon gravity is 1/6 that of Earth. What is the new period on the spring pendulum? It's the same. You should send him a gift basket for saving. Why is it the same? Look, you can interrupt him. He just interrupted her. What? I thought I heard you say something. Well, then why don't you say something? Oh, excellent. Sometimes we do smile upon sniffing. So, what's the answer? It's gravity independent. How do you know that it's gravity independent? Because if you did the homework last night, also, how can you tell from that equation? It's not in the equation. So, spring pendulum is based on 2 quantities for its period. What are the 2 quantities? Mass and the spring constant. If I took that spring constant, oh, I got a live one here. The spring constant on Earth is, I'll make it easy for you. It'll be divisible by 6. Spring constant on Earth is 600. I take it to the moon. Moon's gravity is 1/6. What is its new spring constant? Neurons are starting to fry. You don't know. What is the name called? What is K called? What is the K is what? Spring constant. All right, deer in headlights, I'll move on. So spring constant, what's the key word in the phrase? Constant. Is it spring variable? No. So 100 Newton per meter spring on the moon is 100 Newton per meter spring on space or whatever. Wherever. So simple pendulum. Now this gets around that whole like, we don't have air around these pendulums. So granted, the elephant and the mouse that we have on these pendulums are going to die fairly quickly. So let's answer the question. You have a mouse at the end of a 4-meter length pendulum. You have an elephant at the end of a 4-meter length pendulum. What is the change in the period? It's a simple pendulum, therefore mass is independent, or it's independent to mass, or not mass dependent. So we restore air. The mouse and the elephant are fine. But because there's no m in that equation, it doesn't change anything. What would I have to do to the simple pendulum to double the period? You quadruple the length. If you quadruple the length, L becomes 4L. Square root of 4 becomes 2. And then there you go. How would I also double the period without touching the length of the string? Take it to Mars. G would have to become what? 1/4 G. Because 1/4 G kicks that 4 up in the numerator. Square root of 4 is 2, and then again you get the same answer. So what we're really going over is the multiple choice. It's one thing to understand all of the problems and being able to work through all of it. It's another thing to understand and really get into the problems. If I change this, what happens to this? Is this equation based on something? Etc. So those are the two types. And these types of oscillations if you had like they do these at exploratoriums, little science museums. They have a funnel of sand, and that sand just kind of bounces back and forth, and there is a piece of paper going down, and you see that the sand creates this certain pattern, and this pattern is labeled. You have A for amplitude, and then P for peak to peak. Now, in terms of, back it up. In terms of its usefulness, I've always thought it's like, I mean, why get peak to peak? Because the only thing you're going to do is take peak to peak, divide by 2, and then you get amplitude. And that's exactly the reason why you need peak to peak. It's because this line is always, or is not always evident. But you could definitely tell where the highest of the peaks are and the lowest of the troughs are, and you can measure that distance, and that distance is your peak to peak. So for practical purposes, measuring peak to peak is far more valuable than just trying to get the amplitude outright. The other thing is, if this is a distance, no, not L, X, and then this was displacement, then what would happen is this distance and that distance there is the wavelength. If we were measuring time, we would get period. Wavelength is the distance between consecutive troughs. or wavelength is the distance between consecutive peaks, just as the period is between consecutive peaks or consecutive troughs. These have a relationship that if you took the wavelength of these waves and multiplied it by the frequency, you could get the velocity of the wave. And so you could do this by getting the velocity of sound in air. You could get the velocity of sound in rock and all sorts of things. And one of the things that we're building up to is sound. Sound can be created, and really let's talk about waves in kind of a generic term. We've seen, like if you have a rope, a rope has physical displacement. Rope goes up, rope goes down, rope goes down, rope goes up, etc. And this is an example of a transverse wave. The wave that you create when you're playing hopscotch, or not hopscotch. What's the game where you? Jump rope, duh. When you're doing the jump rope thing, that is a transverse wave. And one of the things that you could sit there with this transverse wave is you and your friend can shake it, and you notice that if each of you hold your ends, you can get it so that the wave goes up and down like that in a very nice fashion. And then one of you can continue to shake the jump rope, and eventually you get two of these. And what you begin to notice is that there are points on this rope that move a lot, and then there are also points that don't move at all. And what these are, the points where the rope doesn't move is a node. And then points where the rope moves the most is an antinode. So for something like this, there are two nodes and one antinode. Here, there are three nodes and 2 antinodes. And this can go on. I mean, you could even shake it even further where you get something like this. And you start to see the pattern where the number of nodes is always one more than the antinode. The nodes are where the rope is fixed. The antinodes are where the rope is allowed to move the freely, not only freely, but move the most. And one thing that you can take a look at and just observe is this first wave here is only half of the wave is being shown at any time. It's either on the upper part or on the lower part. So lambda is equal to 2L, or L is equal to lambda over 2. If we go to the next one, lambda is equal to not 2L, to L. And you start to see a little bit more of a pattern form. And that is let's see. That the frequency of the oscillations yeah, NV, I'm about to explain. The frequency of the oscillations is equal to NV over 2L, where N is the order of the oscillations. And V is the speed of sound. In string. And when we're looking at this, the associated N's are n is equal to 1, n is equal to 2, n is equal to 3. You can associate these with the number of antinodes because n is 1 antinode, n is 2 antinodes. Or you could say that the number of nodes is n plus 1. 1 plus 1 is 2 nodes. 2 plus 1 are 3 nodes. 3 plus 1 are 4 nodes. And so you can describe all of this really well. The going into this equation with a little bit more detail, the frequency is NV over 2L What is V? Well, V is the velocity of the wave within the rope. That rope, the information, the energy within that rope moves with a particular speed. And that velocity is the square root of T over lambda. Now, just as a quick review, this particular semester we're treating rho as volume density, sigma as surface density, and lambda as length density. In other semesters and in other textbooks, sometimes you will see rho sub L. But what we're going to try to do is simplify things and just say lambda. That lambda is your mass length density. Now, when we have this, let's plug this into here. So I've already said that lambda is mass length density. T is the tension in the string. So what I need you to do with you guys right now is let's think about that equation for a moment. Now, many of you have or continue to play guitar, to play piano, and with this equation we can see so much of what goes on in a piano. If you had a high mass length density, are we talking about the fat strings or the thin strings? The fat strings. And so don't think about this equation for the moment. Think about when you're just opening a piano and taking a look inside or looking at the strings on a guitar. Which are your lower pitch strings? The what? The heavier ones, the fat ones. So the fatter strings are the lower pitch strings. The fatter the string, the thicker the string, the lower pitch, because lambda is in the denominator. So as lambda gets bigger, F gets smaller. Now, what's another way to change the frequency of your guitar string? Tighten it. So if you tighten your guitar string, what happens to the frequency? It gets higher, yes. So if you tighten your guitar string, tension gets higher. Tension's in the numerator, therefore your frequency gets higher. If I wanted to lower my frequency by using only tension, what would I do? You would what? Lessen the tension, yes. So lessen the tension, lower the frequency. Like if I wanted to double the frequency, would I double tension to double frequency? No. No, no, no. Ooh, I got passion over here. What would you do? You would use a different string.
I mean, if you double tension, it's going to snap the string.
Okay. The deal is, the strings are made of rebellion. They can handle it. You would quadruple it. Quadruple the tension would double the frequency. Also, what you notice about piano strings, the high frequency strings are on the left side or on the right side of the piano. They're on the right side. Those sides have the shortest or longest strings. Shortest or longest? They have the shortest. When you look at a piano, the lower keys are on the left. Lower keys mean they have the longest L to produce the lower frequency. So lower is on the left, longest is on the left, higher pitch is on the right, shorter is on the right. And so you'll start to notice that. Stand-up pianos, you can't really tell unless you really crack that thing open. But for baby grands and grand pianos, it's quite evident.
Where did you get the velocity of the curve? That is an equation we need to know.
That's an equation that you need to know. You need that one up there on the upper right? Yeah, that's it.
Okay.
You need to know.
I thought you knew.
No. This isn't too loud. All right, now let's play a game with a guitar string. The numbers, dynamically making physics problems is always fun. A 50 gram 0.4 meter string is tightened to 5,000 newtons per meter, or not, that's not a tension, that's a spring constant. 5,000 newtons. What is F if N is equal to 1? So we have a 50 gram string, 0.4 meters long, tightened to 5,000 newtons. What is the frequency if N is equal to 1? And this is your type of problem written all over. It's a plug and chug. You should just be happy. So F is N over 2L square root T over lambda. N is 1, L is 0.4, T is 5,000, lambda is 0.4, or I'm sorry, no, what did I do wrong? I did give you everything that you need. What was my original, what did I make a mistake here? I thought lambda was wavelength. What does this lambda mean?
Lane density.
Linear mass density, correct. So that linear mass density is 0.05 kilograms per 0.4. And that is one of the dangers of using linear mass density as lambda, because sometimes you get it confused with wavelength. Yes? This lambda down here is linear mass density. And I want you to, as well as this, the biggest thing that it comes into conflict is wavelength. So you need to understand the context in which that lambda is being used. If it's lambda f is equal to v, that lambda is a wavelength. If we're talking about a lambda down in here, that's a linear mass density. So getting to this, ooh, I feel good numbers coming on. I got 250. Yes, the wrong number.
I was using my phone calculator, so I was like,
Yeah.
I'm going to do each piece separately.
When I saw that it was going to be the square root of 40,000, I knew, yeah, we're into it. All right, so the frequency is 250 hertz. And that is the, you pluck a string with those conditions, its N1 value is 250 hertz. Question?
So in the equations that are like v is equal to lambda over 2 or v is equal to lambda, that's the way that happens.
Yeah, then you're going to use the wavelength stuff. Linear mass density, yes. Okay, now, let's go over, now this was for n equals 1, but there can be other types of n values. Actually, I'm going to write on a new sheet of paper. N equals 1, 2. There are naming conventions. The first type of naming convention is the harmonic convention. The second type is the overtone convention. The harmonic convention is fairly easy. N equals 1, first harmonic. N equals 2, second harmonic, and so on. When you're dealing with the harmonic system, it's always the nth harmonic. Find out what value of n is, and then you can go on with there. For the overtone system, it is the fundamental frequency. Oops. I bring my battery all the way over here to not use it. Fundamental frequency is the first harmonic, n is equal to 1. For the overtone system, first overtone. The first overtone is the first overtone over the fundamental frequency. Then comes second overtone, third overtone, fourth overtone, and really what this is n minus 1 overtone. So if I said this harmonic is your third harmonic, you would know that n is equal to 3 and your overtone was the second overtone. What is the n value for the fourth overtone? The n value for the fourth overtone is not 4. It is 5. If I was dealing with harmonics, say, what is the n value of the 803rd harmonic? 803. So, and so these are for so we have this. Now there is another type of production of sound, and really when you think of sound, they're longitudinal waves. With longitudinal waves, the high density is high amplification, or amplitude. And the best example is sound. The sounds coming out of my mouth are causing the air between you to compress and the air after that to compress, and eventually it gets to your head and then it squeezes into your ear. It's not like the air directly from my mouth is getting into your head. That would be creepy. But the way the energy that I've set up is emanating outwards and reaching to you. Now, in this way, we have some pipes, and this is what I would call a full pipe. Pipe open, pipe open, both ends. And for something like this, the frequencies are NV over 2L. Now, L is the length of the pipe. The N is the order of the sounds. And then V is the speed of sound in air. Now, in physics, we're very familiar with whiteboard physics and lab physics. We understand that in this particular room, G is 10 meters per second squared, because the equations that we work with, the numbers just work better. When we're in lab, G is 9.81 meters per second, because that's reality. In class, the velocity of sound in air, I don't have the equation on me right hand, but in Physics 213, the velocity of sound in air is going to be 350. It's going to be a little bit of a warm day here. The velocity in a lab is I think it's 33. Don't write this down. 331 and some change plus 0.5 t is this. And what will happen is the TA will give you this equation, and you will determine your own V. But for our particular purposes, for the sake of having the numbers work out really well, in class, I'm more interested in you understanding the equations rather than you getting the speed of sound in air experimentally dead on. So in class, this will be the constant. So if we had a pipe, and let's say the pipe length was 3 meters, those frequencies, it will be 1 times 350, 2 times 3, 2 times 350, 2 times 3, 3 times 350, 2 times 3. And so we end up with, oh goodness, 58.3 hertz. One 6.7 hertz. And 175 hertz. And so F1 would be my first harmonic, or my fundamental frequency. F2 would be my second harmonic, or my first overtone. F3 would be my third harmonic, or my second overtone. And so those would be the frequencies. Now, I call this a full pipe. Some people just say pipe open at both ends. Either way is fine. My naming convention for the next type of pipe is a little bit unusual, but it is necessary because we're going to be doing a lab on this. It's called a half pipe. With a half pipe, it is merely a pipe closed at one end. And when you really look at the behavior of a half pipe is just a pipe that's twice as long. The behavior of this pipe and that pipe are the same. And we can go into some derivations and show how it's so, but we're not. The frequencies of these half pipes are NV over 4L. The thing that we've noticed for full pipe and string is that N is equal to 1, 2, 3, not 5, 4, 5, etc. The half pipe allowed is 1, 3, 5, and 7, etc. So the big differences between these, so for full pipe and string, N is 1, 2, 3, 4, 5, first harmonic, second harmonic, third harmonic, fourth harmonic, fifth harmonic. Or you could say fundamental, frequency, first overtone, second overtone, third overtone, fourth overtone, and etc. For the half pipe, the N values are 1, 3, 5, 7, 9, etc. Now the harmonics are always based on N. So it goes first harmonic, third harmonic, fifth harmonic, seventh harmonic, ninth harmonic. Even ends are not allowed. So if you have a pipe closed at one end, and I say, well, what's the frequency for its second harmonic? Exact. It does not exist. For the overtones, the naming convention for the overtones is like this. It just goes fundamental, frequency, first overtone, second overtone, third overtone, fourth overtone. Because by definition, the overtones are whatever the next overtone for harmonic. So if it has a frequency, yay, it's the first overtone. Oh, there's another harmonic. Yay, that's the second overtone, and so on. So the overtones don't skip. So the overtones don't skip, and you can
Can't use the N-1 for that case.
no, not really. I tend to just count. All right. In terms of your what's in it for me, next week is we're doing the speed of sound and air. And that one is gonna be a little bit of a problem. We do not use, oh my goodness, if we had 12 of these things going off at the same time, that would be a problem. What you do is, you have a tube filled with water, and there is a little tube at the bottom, and you've got a bucket, or not a bucket, you've got like a little water reservoir. And if you want the water to fall, you lower the bucket. If you want the water to rise, you rise the bucket. And this distance here is that L that you use in NV over 4L to get your frequency. Now, how they recommend it is you've got your tuning fork. Should have brought a tuning fork. You take the tuning fork and they give you a little rubber mallet, which is on a little steel hammer thing. And you take the rubber mallet and you bang it at the end of the tines. And then you briefly touch the bass. Like if my harm was the tines, you briefly touch the bass, and that gets rid of the overtones. So when you see a tuning fork that says 500 hertz and you bang it, it initially produces frequencies of 1500, 2000, etc. To get rid of those overtones, you touch the base of the tuning fork, and that dampens out the overtones. Now, how I normally do it is what you do is you take that tuning fork and you bang it off your patella. Because the patella is just a nice big wad of hard bone. Be sure not to pop it off the tendons. Go right after the hardest part. And that will give you a much better amplification on your tuning fork, and then you tap it out. These tubes are on the order of 1.1 meters long. What I recommend to the students is, in the instructions, they say you bang it, you dampen it, you put it over the water, and then you start lowering the water. And when you reach a resonant point, the water will resonate. And so if my hand is the level of water, and let's say that's where it's going to resonate, it's going to go, and you'll really hear it. And this is also one of the reasons why we're only going to have 4 or 6 of these things, because having 12 tuning forks banging away will give you a headache. So there'll be fewer numbers. My recommendation to you is, if you have a tuning fork let's say you had a tuning fork of 500. And those frequencies, NV over 4L, and V, you can kind of play with the number a bit. You could say 340 or 350, it doesn't really matter. And what you're gonna do is you're gonna look for L's. And you're gonna pick 1, 2, 3, 4, maybe. So if N is equal to 1, L is 1 times 340, 4 times 500. This 500 is whatever's written on your tuning fork. It could be anywhere from like 280 to 600. And that gives you an L of 0.17 meters. Now really, all this is, the 0.17 is this. So L is N times 0.17. So N is equal to 1, L is equal to 0.17, N is equal to 2, L is equal to 0.34, N is equal to 3, L is equal to 0. Times 3. Human calculator, you failed me. You said it, sorry. Multiply by 4, what is it then? 6/8. Okay. All right. So really, we've gotten to the point where it asks for 3, if not 4. And all 4 distances are available. And what you do is you mark those distances and so this is for the 1, 2, 3, and 4. Now what you're going to do is you're not going to have the water right at the top. It's not going to resonate right at the top. What you're going to do is you're going to have it down at about 12 centimeters. And if you know this thing is going to resonate at 17, start at 12, 13, or 14, and then lower the water and then rock it back and forth right where you think it should be. And then you get a more precise measurement. Because as you bang that tuning fork, the amplitude of the tuning fork gets weaker with time. So you need to have a very strong tuning fork so you can get a very pronounced resonation. And that's what happens. You don't start at the top and go down to that one or that one. For this one, you start at about 48. And you go from 48 to 53 and back and forth until you nail it down. And once you get all of those, then you can get an average for the speed of sound in air. And so it's a rather fun lab, it's a rather quick lab, it's a very quick lab if you follow these procedures. Yes? I do say that, which means now I've jinxed the class, and you guys will be there in Dead Week doing the same lab. All right, that's it. See you Thursday at 8.
Are you gonna post this after?
Yes. Yeah, I will post it.
Before?